You've got a mastering. It's due tomorrow night. Okay. Well, what?
Tonight or tomorrow?
I think it's the 9th, right?
Yeah, you were talking to people yesterday because it says on the
I literally
map
just sacrificed my
on
food.
the board tonight. And then you said tomorrow night instead.
Doesn't it say the 9th on master?
Yeah, but it said tonight on the board.
No, it doesn't.
On the,
Doesn't say anything on the
on
board.
the whiteboard, it said that it was muted.
Yeah, I have a picture. No, you're a liar. No, I think I deleted it. No.
Fake news. All right, so it's due tomorrow night. If you have questions on it, I would come in during after today because my kids are on the way to school today, so I'll get going with her tomorrow. And then there's another mastering that's due Saturday night. Okay, except everybody tell Mara it's due Friday night. And that's more like problem solving stuff. The book problems in this unit are not quite the level that I want them to be at. Okay, because in the book this is chapter 2. This is like early doors, and it's just kind of like I don't know. Physics is stupid. Like a lot of places just teach projectile motion straight out the gate, but you have no context for understanding why the thing is moving as it is. Clearly, I like where we're sequencing it because you know CVPM already, and you know CAPM already, and you know BFPM, and you know UBFPM, so you can kind of make sense of what the projectile is doing. Okay, and I kind of like that aspect of it. So, long story short, the mastering that's due Saturday is not quite as challenging as I need it to be. So we're going to work on some nastier stuff in class, and I would anticipate I can go ahead and put it up there. The test Wednesday of next week, maybe. Probably, because it's just not a very beefy unit, all right? So 9 plus 7. Yeah. 16 is how math works. All right.
You don't know the phrase like
All right. Yesterday you got the velocities of the launcher on the different settings. Okay. TIL. Abril, if you turn around, can you read what it says there above projectile launcher on the side of that thing? Short range. So we bought 3 of the crappy ones, which is really disappointing because like our old ones are the long range ones. So I might take them home tomorrow and swap out the springs. Because yeah, they're just like they're not exciting at all. The thing's not shooting fast enough. What did you get for the low velocity yesterday? You took a picture of it, right, Mara? So look on your phone quick. You took a picture of your board before you erased it. So somebody check it on your phone. Somebody grab a whiteboard for your group, okay? If there are some. Looks like there's 1 or 2 whiteboards in the back. You can maybe grab one of those. All right, so launcher, low velocity setting, 3-ish. What do you got? 3.1. Okay. Yeah, you can erase those. Yeah, I had to Frankenstein it out of 2 broken ones. It's really exciting because one end of it is right-hand threaded, and the other end of it is left-hand threaded. Is your special pin left-hand threaded on the nose cone? Like I was trying to get the nose cone off and I couldn't, and then I tried the other way and it worked. All right. So, in your sort of schema for solving projectile motion problems, you need to build a flow chart. And the flow chart kind of works like this. There's a type of projectile problem that we dealt with yesterday. The coins or the launcher as it was yesterday, where it launches everything flat. Okay, it starts out initially with the motion all horizontal. What I'm going to do right now, though, is I'm going to flip that 90 degrees, and we're going to, instead of shooting it straight out, we're going to shoot it straight up. going to have an initial velocity of 3.1 meters per second. And what I'd like you to figure out is the max height, because then what we're going to do is, it was Cal, right? He's got the helmet with him today. He brought that with. Good thing. We're going to put that helmet on him, and we're going to have him hover his face above the launcher just to verify that it doesn't go any higher than that, okay? So that's what you're figuring out right now, is the max height that it reaches. So we know it's going to start off on the low setting with velocity of 3.1. So draw the VXVT and the VYVT graphs. What are those going to look like? Figure out how high this thing goes.
The highest point is going to be the area that it travels till it reaches zero. So that should like
Well, what's 9.8 times 17? What's 10 times 17?
VX is just
165.
What's 9.8 times 36 and a half?
365, 36.
Then you wouldn't be at West High.
Oh, yeah.
Your locker would say the score leads.
Those are weird. They had the cutout.
Liberty did that too. That's why we have to have 30 people per class. West High, pretty on the inside.
We're like,
So again, I'm just a boy standing in front of a room asking you to draw BYD2 graphs and think about what represents the maximum height it's going to reach. Practice for the maximum height some other time. Michael, what's your competition? Saturday. I thought it was like, I thought we were going to watch some live stream. Oh.
okay, that's it. So how high is this?
So this is acceleration rate.
Yeah, you can just put
We're 4.9. I just. No, Austin, you just sit there and look at the triangle for a while.
Hey, I'm the one that gets to be sassy in here.
Oh, that's Thomas, give me a calculator.
So this is
Yeah, that was pretty
3.1. Yeah.
I'm trying to go faster. See, that's
3.1 minus
like
10.
when I'm famous and people are like asking for money.
Yeah. Where are you going?
Yeah. As long as they all look that. There you go.
So it's
Yeah.
3.1.
Yeah.
I'm getting longer. It's not that bad.
Oh, welding mask. Yeah. Okay.
You got to follow us on that.
Okay, so it'd be
Gotcha. No, famous politician.
That was a-
How about you make like
We
do that too.
Not sure how fireproof.
I was like, wait.
From the 70s,
And then-
probably highly.
Yeah, the area
It's
that-
such a politician that wanted to
There we
do for the people. Just not in a country that he was in. Just that people wanted to.
Complex hockey doesn't need to.
Yeah, you're right.
Thanks for updating my grade folder.
Try.
It's a lot.
Oh, your test. Yeah.
Look, there's a secret message within my phone. You gotta find it.
Hey, once you got it, can you flip your board to brown so I know we're ready to move on?
So, we're not ready.
We'll see you guys over there.
This is,
I said no one knows that. That was your secret message.
so, Ricky, like around
Yeah.
We need to enlarge it.
Confirm.
Or if we want to burn small living creatures with the
I
sun.
used to do that. I find like little mushrooms.
Oh, okay, mushrooms. I thought you were going to say like.
How could you, Eric?
Or dodge, there are rules here.
Wait, does it work only with the sun?
So you try yourself.
Eric, I give
Flashlight
you
with the sun.
Or like,
No, it is not true. I just did mushrooms. Well, mushrooms are. Yes.
Going to fun guy.
Eric, what are you doing?
Eric,
You don't want.
All right. We'll let the sorting hat pick some group to come tell us what the answer is. All right. Boop. Charlie and friends. Come on down. Talk to us about where we're putting the face. Oh, perfect. It's Kyle's group. I saw a flashlight from over that way. I had no idea what it was. Now my retina's burned, but hey, at least you tried. All right. So, where are we going to put Kyle's face? Shoosh. They've got a small board, so you're going to listen really hard.
So at the time that it reaches its maximum height, the velocity is 0. And we know the initial velocity is 3.1 meters per second. So the change in velocity is going to be negative 3.1 meters per second when it reaches the maximum. That means that to find time, we need to divide negative 3.1 meters per second by the acceleration, which is negative 9.8 meters per second squared. And that gives us time equals 0.32 seconds. So we know it takes 0.32 seconds to get to its maximum height. And then we find the area under the velocity versus time graph to find the distance. So d equals 3.1 times 0.32 over 2 equals 0.50.
So you got half a meter basically. All right, so let's check it out. Actually, we probably don't need a chair. Kyle, coming back here. Ball. And we're gonna put his face at the 0.5 meter mark. So right about there. Okay. What?
About this half a meter from here.
Oh, he's remembering that whole part about plus C. So we're finding the area under the graph. That's the change in height, not the absolute height. So he's wanting me to measure that 0.5 from where it starts, not the table. Okay, so there. Okay. And I use your hand to like hold that. Sometimes it'll fall. No, I'm talking about the face mask. There we go. All right, so go like that. Keep your mouth shut. All right. You're moving. Don't move. First rule of physics. Don't flinch. All right. Here we go. Ready? How'd we do?
Pretty good.
Pretty good, right? It's pretty close. Okay. Well done, Kyle. So, if we do it without the cow in the way, 0.5 meters. Whoa. That's really got lucky. You must have backed up. It looks like it goes a little higher than that.
I did.
So there's 0.5. So to the injured finger, it goes just above it, maybe. I'd say about 0.5 feet or so. All right, cool. So that is the type of problem where we don't have to solve two problems because there is no horizontal velocity because it's just launching straight up. So we just draw the Vy graph. The area in the positive part of the graph represents how high up it goes, and then we don't care about it after that in this problem, okay? So kind of be mindful of how that works. What we're going to do next is a type of problem where this thing is going to be angled. I'm going to set it at an angle of 30 degrees. And we're going to put it on the medium setting. What was the medium setting yesterday? What did we get for that? 4-ish meters per second.
4.8.
Oh, 4.8. Yeah, that's it. 4. We got concurrence on that, 4.8? Okay. And then these two physics friends here are out having a good time, doing piggyback rides and stuff. Maybe. Come on, Einstein. Okay? And so we're going to launch this thing at an angle. Now, if I just put them right here, there's no sport in that, right? Okay? So we want to set them at a distance here, and I'm going to leave it to you to figure out what that distance needs to be. Important. Really? So important things to note here. I've got the rock's chest at the same height as the launcher. Okay? So if you think about the shapes of the graphs, that's going to help you a lot with the solution. Okay? What is the Vy graph going to look like if we want to set the rock out here? Come on, the rock. And the ball is going to go like that. Okay, come back down to the same height. So think about what that tells you about the graphs there. And again, you said the launch velocity is 4.8 meters per second. So hey, hang on a second here, friends. So with an angled launch, this 4.8 meters per second isn't going to go on either of our graphs. Okay, I'm not going to put 4.8 on the Vx. I'm not going to put 4.8 on the Vy. What I first have to do is a little bit of trig to break this down. This angle here is 30 degrees. And so we got to figure out how much of that is projected horizontally. That's going to be the Vx. It's going to equal V cos 30 degrees. So 4.8 times cos 30 degrees. And then the blah, 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 Vy. 4.8 sine. Ah, man, this is just in a bad spot. Vy. 4.8 sine 30 degrees. Okay, so when you have a launch at an angle, you've got to use a little right triangle trig to decompose the velocity into the horizontal and vertical projections, and then take it to the graphs.
Yeah. So like the change in y is one. Figure out what is zero. But to do that, we need time.
So when you're drawing the VY graph here, I need you to think really carefully about what the shape of this graph is going to look like if it's going to begin and then end at the same height. Okay, Rock's chest is at the same height as the launcher.
I'm just confused.
Because I just like
I think
did this
the
like
issue is
acceleration.
Yeah.
So velocity of acceleration is so that halfway.
pretty much true.
Yeah.
So 9.49 is the value of the So that's this. Which is half of that. And it goes to like.
Ooh.
That has to be right times this. It's kind of medium, so
Yeah.
we have to use a horizontal. Otherwise, we're fine.
That was
It's
actually
actually 2.0.
It's this game.
For
I give you 2.0.
That's a lot.
Even.
She's been there for 1.5 years.
initials and 4.8. Oh.
Well, what?
This is rather than like Mr.
This?
Kurt's like joking about and like he like me and Thomas like actually
I never think
part of our he thought he couldn't do it, not even like
we got that Spotify.
and like this the rest
Hey, once you got the solution, go ahead and brown side out your board, just flip it.
No. There's two.
Ooh. Remind me to talk about the alternative solution here as well. So does that fit? Ooh, this might. Oh, okay. All right, let's consult the sorting hat. Boop. Mara and friends, pop on up and talk to us about your solution. All right, how's this go?
Alright, so you have like the arrow direction, right? And you put them up into the X and Y components.
Your arrows look like lines.
They're arrows, alright, they're missing. Alright, anyways, so you have the initial Y velocity, which is 2.4 meters per second.
There we go.
Anyways, there's the initial Y velocity is 2.4 meters per second, and its slope is -10. So you figure out the time to hit the peak is 0.24 seconds, so you gotta multiply that by 2.
Why?
Because the peak is not 50 miles. You just do
It starts and ends at the same position, so it's gonna be equal.
So what has to be true? Those two triangles that we have up there.
That has to be equal
So if I add their areas up, what's going to happen?
0.
0. There we go. Okay. So you got that symmetrical bow tie thing. So this is really important to the solution. Okay. So look for that in a problem, because anytime you have a problem where it's like a golf ball that's hit off the ground and it comes back down to the ground, or somebody kicks a soccer ball, or you throw a ball to your friend and they're the same height as you, or maybe it's your twin, okay? However high it goes up, it comes back down that much, so then they've got symmetry. So even though they don't have it on the graph, they can probably tell me the initial y velocity is 2.4, the final y velocity would be, okay? And then you can just kind of solve things out from there. All right, so they elegantly use that to figure out that it's in the air for 0.48 seconds, and where'd you go from there?
So then you multiply it by the x velocity to figure out how far along the x-axis it travels, and that's 2 meters.
All right, so let's check it out here. 1 meter. Conveniently on top of the ground.
Did you get the
All right, 2 meters. I'm gonna give myself a little plus minus here, so I'm gonna put Einstein on top of the rock. There we go. Just trying to give myself a little target. Actually, let me aim this thing quick. Measure twice, cut once, one. Going too close now. Right. Medium setting, yeah? Alright, so it turns out physics only works if you jingle your keys. Thank you. Clap if you believe in fairies. All right. Wow. Well, at least we'll know why this doesn't work. There we go. Okay, cool. So apparently physics sometimes works. Ben and I jingle our keys. Oh, we have very powerful keys. So look for the implicit clues in a problem statement that you're dealing with this type of problem, that it's going to begin and end at the same height. Okay? Which begs the question. You're the question person. So this is what we do when the thing begins and ends at the same height.
Wait, I'm listening to Rachel's talking.
Stop staring at her, Rachel. All right, so this is how to solve the problem when it begins and ends at the same height.
Yeah. What if it doesn't begin and end at the same?
What if it doesn't? Now we made the mistake last hour of trying this with too tall of a person, so we need not too tall of a person. Tomas, if you could put on the helmet, please, sir. All right. We tried it in McCook last hour. That didn't work. Apparently, it's not that powerful.
You can do shots.
All right. We will definitely do it. All right. So, Austin, if you can move your knee there.
So,
All right. And Tomas, if you can stand. All right. So the target on the helmet is 1.65 meters off the ground. Okay. We're gonna set this launcher at an angle of. Oh, what did I tell you to ask me about this before we did that? About the others. Okay. So, guys. So this works at 30 degrees. So count. Reset the rock. Okay. 30 degrees. Yeah? Ooh, and you got the payload. That's fantastic. Oh, they flew too close to the sun. Nice performance. What's going to happen? Medium setting, right? Medium setting, yes? What's going to happen if I change the angle to 45 degrees? What's the ball going to do? Right? Kids that new stuff going in here. So I'm going to change it to 45 degrees. Sorry, Kyle didn't play with toys. All right, so 45 degrees, what's going to happen? All right, Cole, close your eyes. All right. myself in like bird box that. But anyway, all right. So it did what? We missed. We went farther. Okay. So now I'm going to change the angle to. Wait, have you guys read this book before?
Yes.
Sorry about that. Well, what? And you see, it works. Thank you. All right. So, great. Let me cheat slightly. I gotta get this all sorted out for me. Yeah. State of the action. Oh, you didn't have Einstein on top of that. That was my mistake. Right. No, for the sake of the audio recording, we'll pretend Kyle didn't have Einstein on top of it. All right, ready? That's the low speed setting. My first day. All right, here we go. And Einstein. Yes, that's what we. Yeah. Whoa.
I refuse. I do not give you power.
Hold it. Just hold it. Like, I know. Get Einstein on top of it. All right, ready? Here we go. Yay! It worked. We're just audio recording. They can't see. All right. Bummer. All right. It's a new launcher. I'm not used to it. All right. So it should work. 30 and 60 add up to 90. They are fluent angles. Fluent angles. Okay. Anytime you have fluent angles and you get to this at the same height, it should work. So 45 gave us our maximum. Hey, 45 gave us our maximum range. I went beyond 45, and now it's bringing the range back in here. 30, 60 should work. Okay, because there's fluent angles. Okay. But man. There we go. All right, Cal. Let's bury that thing. All right. Thomas, the target is 1.65 meters off the floor. The launcher is 1 meter off the floor. And we're going to use the high speed setting, which is how fast? 6.6 meters per second. And we're going to use an angle of 45 degrees. So that's 1 meter. And then Tomas. That's 1.65 meters. Okay. So the question then is, that's not where I want to measure that to. I just tried to dry erase digital pin. Okay. So can you determine how far back we have to stand, Tomas? So the launcher is 1 meter off the ground, 1.65 meters is his height to the target. There we go. Let's make it more sporting. Let's go for on the way down. Yep. So we're looking to get something kind of like that going on. This is where we find out that his height equals the I'm not used to using those little wimpy short range launchers. This is not.
Well, he's the test.
6.6.
Oh, that's true, that's right, okay. We're not gonna look at the calculations on purpose. Yes.
It's gonna be decided.
Right here, material to the left. It's quite 65.
Yeah, so it's the velocity of 4.7, right? 4.67.
I mean, basically. Oh, it's 4.9. Again, what is these? Every single count, and there's always a new one. There's always a new one. Root two.
More happy race density. Yeah.
No way, I forgot the piece.
So then this one has to be 0.09 equals 1/2 times. Okay. Yeah, so then 0.09 equals 1/2 times. But the triangle's
Oh, sorry. I see what I meant. So then you just divide by root two. That's what that's how
Maybe we could write that more.
So the one going with the wall will be bigger.
I don't know how one, so is that 2.09, so it's just gonna be, the area of this is gonna be, because you add this to the 1 meter, because it's already on the table. So it's gonna go 1 meter near above the table, 2 meters near. It's gonna come down in Thomas area. So the area of this, is coming down. It's gonna be the difference.
I see, yeah. What's that, 1.6?
Yeah.
So this area would be.
So then we have
So we're assuming, yeah, because the height is like here. It's like 7.5. You can't just say it's easy. Right here. So the peak is that.
Okay, so then find out. And then, so that's how long it takes, and then we add new.
No, it needs to cover this because
And the total.
change every 0.5 to 9 here. So when you add this here, it's positive. Yeah. That's how it works. This is. We can get the. That's why I just use my mind. We can use a trail.
Okay, no, I just keep those two.
So 4.6 plus this is.
Thomas, she's proud.
This is 2.
Yeah, they did not get the same. Oh, this I was gonna say. We must place Thomas 10,000 meters down. No one did.
3.5.
I got 6.5.
Or whatever, let's just say.
Thomas is amazing. One on the way down.
So that equals 1/2. Yeah, 1/2.
Just make sure the goes out. Wait, why?
We didn't round quite as readily.
Yeah.
We just got like
Oh, we stored all our numbers left. It might be rounded.
I mean, it's fine.
Thomas is more than 10 centimeters wide.
I don't think for sure.
If it mess up, it's like.
Figure that out.
Why?
Oh, yeah.
So
No, but we can figure out the final velocity in terms of.
We did use negative two.
And then you find the area with you add these two. The area of the triangle going down.
So it's 120. So
Common ordinary 10 seconds.
the difference between that and one. Oh, so then this takes half the time. Yeah. Like the
So
slope
this
is-
shows 1.1.
Yeah, so.
So we need to add
So we want to.
Well, it's just gotta take the difference between.
Too tall.
No, I'm just showing.
That height plus the table.
That's how high it'll be.
Oh.
Yeah, yeah, that's the table.
And then, well, how high is it?
So 0.6.
Yeah, it's high. It's pretty straight. 0.45.
I would say it's not.
Yeah.
It comes with different, yes.
I still think 10,000.
Depends on.
0.45.
Yeah,
I think we should put Thomas like right next to it. Just one side.
And so you're gonna be selling it.
So this, you are.
approval.
You're also designing that.
But my
And then you don't.
And this is
really
It's like, they probably have the same principle.
Oh, that's right.
Right, not looking at unless you love your-
They're both the same graph.
I know.
Oh, no.
I don't have to share. Yeah, you have
Same deal. Once you got it, brown side out it. We'll put the helmet on. Come on.
3.5. What do you guys get? Something like that?
So like.
Yeah. You sit close here. Have a sock.
So it feels like
This is right.
Oh, apparently Asians are smart.
that's the way we read our book for I was like right out there working the rice paddy field, so that makes it smart.
No, do you know what?
That is how much I care about school.
It's like, what do you hope to add? I hope to make the campus safer for all people to do.
Yeah. One good at a time.
Now it's you right now.
Campus.
One time
10 years from now, I'll go back on YouTube. the one that was giving me a hard time earlier about screen tapping. Oh, no. Ah! They're both eyes.
I still remember that.
I still remember the number. Take 100. Are we there yet?
I still remember it. You're like
His father.
Literally ran out of time. That's an indication.
It's like about like the entire day. Nothing. All Henderson does is just lecture at me. And then, okay, we got through one lecture.
You know what the exit velocity is?
Oh, wait, I smell that. Don't worry.
How many who?
Yeah.
Those? Yeah. Yeah.
Oh yeah, you know the snow?
It's like.
Are we ready? Can we shoot Thomas? All right, let's pick a group. And you're gonna have to talk fast because we don't have a lot of time. Boop. Mara's group. All right, sorry. Emma's group. Poofle poof. Come up and chat. Oh my gosh.
I feel like we're just in some
All right, they just erased their answer, but everybody got 3.7. All right, so let's put them at 3.7. Make sure it works. I got it. You can borrow that meter 6.
You're the one that's going.
There is 45 degrees.
Is that not this?
Maybe. Why is that we went with 45 degrees? All right. All right. Are you good? You said 3.7. You got verification?
Might not be a teacher.
Thomas, if you get a concussion.
Can't get a concussion. He's got a helmet, right? That's why we wear helmets in football. You don't get concussions. Aye, somebody better find that ball. Ooh, here we go.
No, we lost her.
Ramrod. Ramrod. Oh, 45 degrees. Oh man, it's a buzzer. Oh, it's just like the Bears. Yeah, I got Boo. All right, hey, I'm gonna go to the Master Workday.
Yeah. Yo, I legit asked Harding yesterday if we have a master word. He's like, no,
Yeah, I got you to play. You're like, kid getting sick. He's been in the car this morning. Oh, I don't like this launcher. The old ones were so much more reliable. Francis, that's gonna be the practicum lab for the shoot. You're gonna throw a marker from your seat, and it has to land in that. Oh, you almost banked it. Woo. Jeez, that's class. I don't like this launcher. I don't. The other ones were like way more reliable. I think it needs to be like broken in.
My brother had a Chromebook before we got Chromebooks. He used it as a frisbee.
How'd that go?
Kind of broke.
It worked just as well before and after.